Hi, my name is Georgi Radulov, and in this video I would like to make a comparison between the PN junction and the two-terminal MOS structure. I will analyze their charges, electric fields and potentials. So let's start with the two structures. Here, this is the PN diode structure, and these two are the MOS structure in depletion region and in inversion region. Actually, the difference between these two is the magnitude of the applied electric field. Here is a moderate and here is strong electric field. The direction is the same.
So let's briefly discuss the structure, the PN junction. What we have here is an electric field, which is the sum of the built-in electric field plus the externally applied reversed bias field. This will give an extension to the depletion region. Almost no current will be able to conduct through the structure because it's in reversed bias. So all the electrons, free running electrons in this area will be depleted, so they will either diffuse to the p side or recombine with the majority the holes, and the same thing here for the mobile hole. So all that remains here is a space charge due to the immobile ions, positive and negative ions of the dopants. Then if we take a look at the charge is actually distributed in space. So this here is the charge due to the negative ions, and it will be extended in an area xp with a concentration of Na, and Na is the concentration of the acceptor dopants for the p side of the semiconductor. We have on the n side the charge, and you see that the concentration of the charge in the n side is shown to be greater. So we can consider here an example in which Nd is larger than Na, or the dopants, the donor dopants for the n side are higher than the dopants in the p sides, the acceptor atoms. And of course we'll be also discussing, commenting on the case when this difference, this ratio is Nd is much larger than Na, or the single-sided junction. You can see here that the depletion region extends mostly in the p side, and this is because Na, the acceptor atom concentrations, are in lower concentrations than Nd. Alright, so in this case, this is especially considered chosen case, so that we can make links to the MOS structure, the two-terminal MOS structure.
So what is the difference in the MOS structure? We have on the right a metal plate, then oxide, and then this is the p-type semiconductor. We apply external field. This field exercises force, drift force on the holes, so they move along the field and they leave behind the negatively charged dopant ions. So here in this region, space charge is available, negative space charge, and the region is depleted from holes, and the holes are the majority carriers in the p-type substrate. So this is then also a space charge region. Similarly to the PN junction, we have also charge distributed in space. Here we have an oxide. This is an isolator, so that there is no current that flows through the structure. And this negative charge here in the depletion region, this space charge, is actually balanced on the other plate of the metal terminal by positive charge. Since this is metal, then the concentration, of course, of charges is very high. So this is the reason why this positive charge is actually in a very thin layer, positioned in a very thin layer. It's not space charge. Then, so this is depletion region. And then this is inversion mode. In inversion mode, we increase the magnitude of the externally applied field, and now the minority carriers, electrons in the P site, are collected within the depletion region, and they form a very thin layer, which we will later call a channel, at the interface between the semiconductor and the oxide. So now if you look at the charge here in the diagram, what you see is that you still have the space charge, of course, so these are the immobile ions, but you have also a thin layer of electrons, which are also negative charges, but they are mobile, so they come they'll come here and pile up here if the applied electric field is sufficiently large. On the other side, of course, the positive charge is increased, and both balanced each other. The name inversion comes from the fact that here in this thin layer at the interface between the semiconductor and the oxide, the semiconductor behaves as an n-type, because in the vicinity of this interface the majority of the carriers are now electrons that used to be minority carriers in the p-type, in the semiconductor. So this is why the mode of operation is called inversion mode, because the interface is inverted from a p-type to an n-type. Now an important thing to note is the balance of charges for all these structures, for the PN structure and for the MOS two-terminal structure in the two modes of operation. Look at the balance of charges. Since in this area and in this area we have charge neutrality, all processes lead to zero electric field. This means that this charge should be absolutely equal to this charge, or NAXP should be equal to NDXN. In other words, the lower the concentration, the more space in space the region extends. The higher the concentration, the shorter in space it is, so that the sum of all negative charges are equal to the sum of all positive charges. The same thing we can see here in the two-terminal MOS structure. On one side of the oxide we have the space charge, which is a very similar expression to what we had in the PN junction, and on the other side we have the positive charge that piled up on the metal plate, which we will later call the gate. So the space charge, negative space charge, is balanced by a positive charge on the metal plate. In the inversion region mode of operation, we have as negative charge not only the space charge, but we have also the negative charge of the electrons that piled up here at the interface. And the sum of these charges is balanced by all the charges that are on the metal plate, assuming that here is no charge, parasitic charge, trapped in the oxide. Now, having the charges, what we can do is we can calculate the electric fields in the structures. For this we use the Poisson equation. So this is the Poisson equation for one dimension, which basically says that if you have a charge in a certain material given with its permittivity, it creates a gradient in the electric field. So this means that if you want to calculate the change in the electric field between 2 points, what you need to do is to integrate the charges between these points. And this is what we do here for the PN junction. This is the charge, and if you integrate this charge, assuming uniformly distributed charge, constant charge, you get a linear function of the electric field. So this negative charge creates a negative electric field. And then the maximum of this electric field will be at the metallurgical junction, this point, and it can be calculated to be the concentration of acceptor atoms times the extension of the region, depletion region inside the P material divided by the permittivity. Then on the other side, the electric field reduces, of course, faster because the concentration is higher. So we assume that Nd is larger than Na. You can see that if Nd is much larger than Na, we'll have here almost minimum
Basal extension of the electric field.
and side. Now let's see how this picture looks like in the MOS two-terminal MOS structure for depletion region. So you see that in the semiconductor, in the p-type semiconductor, the picture is very much similar as the single-sided p-n junction. So we'll have to integrate this charge, and we reach approximately the same formula here. And here we have the oxide, so in space this is the oxide. And if there is no charge in the oxide, the electric field will remain constant. Then we have the metal plate where positive charge piled up, this positive charge, and then the electric field drops. In inversion mode, now we have the thin layer of electrons which piled up in a channel under the oxide. So in the interface between semiconductor and the oxide, we have there the thin layer of electrons forming a channel. So we'll take this layer into account in the integration, and then the extension of the electric field takes place only here. You can see that once we are in inversion mode, the space charge region does not extend anymore. It remains at its extension from the depletion region. And this is because any positive charge on the metal plate can be balanced by mobile charge electrons. So we don't need to extend the depletion region and hence reveal more negative charge to balance the charge on the gate, the positive charge on the gate. This is not needed anymore because mobile electrons, negative charge, can balance any charge on a positive charge on the gates. So these will be the profiles of the electric fields in the p-n junction, in the two-terminal MOS structure in depletion region, and two-terminal MOS structure in inversion region. The last step will be to calculate the potentials, and the potential is of course given by this formula, which says that the electric field with a negative sign is actually the derivative of the potential in one dimension, or the gradient of the potential in one dimension. Again, to calculate the change in the potential between 2 points, we will have to integrate the electric field. So let's see for the p-n junction here. We have a linear function for the electric field. Hence, the function after integration for the potential change is quadratic up to this point, and in this point the function changes, so the curvature of the quadratic field, the curvature of the quadratic function also changes. You can also calculate what is the potential change per side, so this is in the p side. This is just by solving this integral and taking initial condition that, for example, this is potential 0. You take it as a reference. So now the sum of these changes in the potential inside the P region and inside the N region will give the potential change or the potential barrier between the P and the N side. And this will be the built-in potential plus the externally applied reversed bias voltage. What's the situation then for the two-terminal MOS structure? As we expect, in the semiconductor, in the P-side semiconductor side, the processes follow very much our analysis inside the P-side of the PN junction. So we integrate the same linear profile here and we get the same quadratic profile of the change of the potential. At this point, we are now in the oxide. So here is the oxide. This is the thickness of the oxide. And inside the oxide, the electric field is constant. Hence, if we integrate it, we will have a linear function. Then, at the interface between the oxide and the metal, we have a layer of positive charge, which will actually set the electric field to 0, and the potential will remain there. So two things that are important here to note. Any potential difference between deep in the semiconductor and deep in the metal, so in the metal plates, is actually given as a voltage drop inside the semiconductor and voltage drop across the oxide. Now, if you increase the externally applied voltage so that you get from a depletion region into inversion region, here at the semiconductor there will be not much change, because when you increase the inversion, your charges are now at the interface, negative charges at the interface between the semiconductor and the oxide, and positive charges at the interface between the oxide and the metal plate. So this is where charges now in inversion pile up, which means that the potential change inside the semiconductor will remain almost unchanged. And then we see the same profile here. And then any further voltage increase will result in a voltage drop across the oxide. So now, having analyzed these potential changes, let's go back to the PN junction. We can calculate actually the extension of the depletion region. So the extension in the P side plus the extension in the N side will give the width of the depletion region. And then you can easily calculate it because, of course, you have an expression for the potential difference with respect to the spatial extension and the concentrations. And of course, you know the relationship between NDXN and A and XP. When you put all this in the formula, you can express the width of the depletion region to be dependent on the built-in potential difference plus the reverse bias voltage, and here the concentrations of doping in the N side and in the P side. So we consider now the case when the dopant concentration is much bigger than the acceptor concentration. So if this is the case, we have single-sided junction, and here we'll have almost no extension, so Xn will be almost 0. So in this case, here we can ignore Na because it will be much smaller than Nd, and then Nd will cancel with this. And this will be then the formula for the extension of the depletion region, which will be almost O inside the P side junction. Now, this will be very similar expression to the extension of the depletion region inside the MOS two-terminal structure. And the formula is given here. So this variable, this parameter phi s, is the so-called surface potential. This is the potential that we have at the interface between the semiconductor and the oxide with respect to a reference point which is deep in the semiconductor. So actually this is giving this gives the bending here of the potential inside the semiconductor, phi s. And from here you can calculate what is the extension of the depletion region. Why is this important? Because if we reach certain maximum value, which is the end of the depletion region, at the border between depletion region and the inversion region, this voltage drop or potential drop will remain the same, unchanged in the inversion region. So this will not change. The size of the depletion region will not change, and the amount of bending will not change. Any further voltage increase in inversion region will result in a voltage drop across the oxide. As you can see, there are much similarity between a single-sided p-n junction and two-terminal MOS structure. Thank you very much for your attention.